In this video, we'll be looking at the mole unit, which is our first real kind of chemistry exclusive unit. And this is the very beginnings of being able to use the mole. And you're going to find that you end up using the mole for almost all sorts of chemistry calculations. So first, before we get into talking about the mole, let's talk a little bit about the idea of counting by weighing. So I'm going to give you a non-chemistry example to kind of illustrate this idea. What I want you to do is imagine you own a factory. In this factory, you produce small hardware pieces. You're going to make things such as nuts, bolts, screws, washers, all those little hardware pieces that connect everything. Now, in this factory, you receive a lot of orders and therefore lots of pieces. You're frequently receiving orders for tens of thousands of these pieces at a time, maybe hundreds of thousands. How do you go about fulfilling these orders? Would you count them? Well, you wouldn't count them. You're the owner, but you might pay somebody to count them. But how long would it take to count out all of those tens of thousands of pieces? Well, you probably wouldn't have somebody count them the way we would normally count things. You would probably count them by weighing them. So you might take out a sample of one of the nuts or bolts or screws or washers, weigh it, figure out what one weighs, then you could just start dumping these onto a scale to figure out what weight you would need to get your order for 10,000 or 20,000 of these pieces. Well, those small manufactured pieces sometimes aren't all identical. So you may recognize this. So you worried about, well, what if that sample one that you chose to use as the representative weight was a little bit light? Well, than average. Well, if it's a little bit smaller than average, well, that's a little bit of a problem because, well, you'd be giving the customer more than they ordered, which isn't a problem, but as a result of that, you're losing inventory you don't need to lose. Well, what if the little piece you used as a sample was heavier than the average? Well, if it was heavier than the average, then you do have a real problem because then when you pull out the weight that you want, it won't have the correct number of pieces. So instead, what you might do is, knowing that they might not all be identical, you may choose 100 random ones. Well, 100 random ones, most of them are going to be identical, but you're going to get the occasional smaller one, lighter one, and the occasional heavier one, and you're going to get a better representation. If you need to do this procedure for small hardware pieces, nuts, bolts, screws, washers, you would definitely need to do this for smaller things like atoms and molecules. Those are so much smaller that you're never going to count out those huge numbers of items. And just like all the little hardware pieces aren't identical, even for an element, we know we have different isotopes. The average for carbon is 12. If you chose 13 to be your representative thing, you'd have a problem, or 14. So that's why we kind of think about averages of these, especially when we're dealing with that many number of individual pieces. So I wanted you to think about this idea of counting by weighing in a non-chemical way, kind of thinking about a whole bunch of nuts, bolts, screws, and washers. You need to do that for tens of thousands of pieces. The numbers you're dealing with that for things that are small like atoms and molecules is even much greater. So here we're looking at the mole unit. That's going to be our counting by weighing type unit. So first off, the mole though is a counting number. Now it's just like any other counting number. It just happens to be a very, very large counting number. 1 mole is 6.02 times 10 to the 23rd. Pretty big number. But that functionality is really no different than some other things that are a little bit more familiar to us. We're familiar with a dozen. It's really no different than a dozen. A dozen is 12. It doesn't matter what that dozen is of, whether it's donuts, eggs, pencils, erasers, cans of soda. It doesn't matter. A dozen is always 12. A mole is always that counting number. But because that number is so large, it has limited practical uses. We can count up to 12 for a dozen. We can't count up that high. That number is just too big for us to use. But besides the counting number, it also has a counting by weighing definition. That we can now use in a much more practical way. And this counting by weighing definition is related to the AMUs we see for the elements, those atomic mass units. So when we looked at something like carbon, we said the average mass was 12.011 AMUs. Well, that 12 AMU average mass for carbon, instead of those atomic mass units, those kind of made up units that got us down to that small scale, now has a counting by weighing definition. The counting by weighing definition is, instead of AMUs, it's that many grams of carbon. 12.01 grams of carbon is 1 mole of carbon. We call this relationship that it takes 12.01 grams of carbon to get a mole of carbon the molar mass. The molar mass is kind of what it says. How much mass does it take to give you 1 mole of that substance? So that gives us a counting by weighing definition. Now we can count things that are really, really small, like atoms, by weight that we can easily measure, as opposed to individual counting numbers. So this works for the average masses you see for all the other elements as well. You look at something like phosphorus on the periodic table. When its average mass is 30.97, well, that's the molar mass of phosphorus. That's how many grams of phosphorus it takes to give you 1 mole of phosphorus. 40.08 grams of carbon, well, instead of AMUs, 40.08 grams of carbon is 1 mole of carbon. So what this does is this now gives us some more meaning to the periodic table, some more uses. We talked about the periodic table before, kind of organizing the elements in groups and periods, metals and nonmetals, but now this does even more. The periodic table is now one gigantic unit conversion chart that you always have available. And being you always have that available, you can use it for a whole bunch of different things. The periodic table has all the average mass numbers, some of the ones we already talked about: carbon, phosphorus, calcium. You can do this for any of the elements out there. Those average mass numbers that you're seeing are now the molar mass. It's how many grams of that substance it takes to give you 1 mole of that substance. So we're going to work through some examples of showing this, but periodic table now just became even more useful than it was already, because now we can do calculations with the information on that periodic table. So we saw that we had 2 definitions of a mole, that the mole kind of was a counting number. That's 6.02 times 10 to the 23rd. Well, if we're talking about something like carbon, 1 mole of carbon would be 6.02 times 10 to the 23rd atoms of carbon. We also saw that the mole had a counting by weighing definition, 12.01 grams of carbon. So one way of thinking about this relationship is I kind of made a pyramid or a triangle, and I put moles on the top. And I kind of put moles at the peak of this because moles do a good job relating to counting numbers. We have a way of relating moles to counting numbers. How do we do that? Well, that relationship between moles and counting numbers, this one right here, to go back and forth between a mole and that counting number, you would end up using the definition of a mole. 1 mole is 6.02 times 10 to the 23rd. That's Avogadro's number. So that's how you would go back and forth between moles and counting numbers. We also saw that moles can relate to grams, that moles have that secondary counting by weighing definition. So if we want to talk about the relationship between moles and grams, we can talk about this relationship between our moles and our grams. Our moles and our grams, well, how are we going to deal with that? Our moles and our grams are going to work from using the periodic table. So if we want to go back and forth between moles and grams, we want to do this conversion between moles and grams. How are we going to do that? We're going to look at the periodic table. That's where we're going to get those relationships from. Okay. Now, one part of this pyramid that you're not seeing, that I didn't connect, you're going to notice that I did not connect counting number and grams together. You don't see any connection running between here. The reason why you're not seeing any connection between there is because we really want to work through the mole. If you try to connect counting number to grams, what you're going to be dealing with are crazy small numbers that are going to be different for every element that you're working with. So we don't go directly between counting number and grams. We always go through the mole. Why? We still have to use one crazy number, but it's always that same crazy number. And it's very large, but being it's only one, you don't have to deal with a whole bunch of different very large or very small numbers. So if you wanted to go from counting numbers to grams, you would go through the moles. If you want to go from grams to counting number, you would still go through the moles. You wouldn't try to do that directly. And there's conversions for each of these steps. First conversion is using that counting definition of the mole, the 6.02 times 10 to the 23rd. You might have been familiar with this as Avogadro's number. If you're going between moles and grams, where are you getting that information from? You're getting that information from the periodic table, those average mass numbers for each of the elements. So what we want to do now is we want to look at some example calculations of doing these. So we're going to do some examples. So our first example is diamonds are made up of pure carbon. So if a diamond has a mass of 315 milligrams, how many atoms of carbon are present in that diamond? So we got a diamond, it weighs 315 milligrams. How many atoms of carbon are actually in there? So we're using a dimensional analysis method, okay, where we can real easily show numerators, denominators, multiplication, and division. We're going to focus on the units. Well, what are we starting with? We're starting with our 315 milligrams. Well, 315 milligrams, I can't do much with that. I know if I ultimately want to get to atoms, I'll have to be in moles, and moles are going to come from grams. So our first step is going to be a milligrams to grams conversion. 315 milligrams of carbon is what we're starting with in our numerator. We want to convert that to grams. So the relationship between milligrams and grams, 1,000 milligrams, 1 gram. We see milligrams in the numerator, milligrams in the denominator. Those milligrams of carbon are going to cancel. Remember, I kind of set this up as a table, but this is really one gigantic division bar when we're doing dimensional analysis. Numerator, denominator are going to cancel. Now I have grams of carbon. Now, from that previous slide that we looked at, we can relate grams to moles. How can we relate grams to moles? Grams and moles get related to each other through that information on the periodic table. You would look up carbon on the periodic table. You see that 12.01. That molar mass of carbon, that 12.01 grams of carbon, is how much it takes to give you a mole of carbon. Those molar masses, we are able to use those as conversion factors to use in problems. So I have the grams in the numerator. I want to go away from the grams. So I want the grams in the denominator. So 1 mole of carbon is 12.01 grams of carbon. Grams of carbon in the numerator are going to cancel with the grams of carbon in the denominator. So now I'm at moles of carbon. So for moles of carbon, now I'm one step closer to my goal. Remember, I ultimately wanted how many atoms of carbon I have. Well, that relationship uses that actual just counting definition of the mole. 1 mole is 6.02 times 10 to the 23rd. Well, in this case, if we're dealing with carbon, that would be atoms. So I look at moles of carbon in the numerator. I'm going to put the moles of carbon in the denominator so they cancel. The only unit I have left is the unit I want, which is the atoms of carbon. All my other units have canceled off. So now we're ready to actually do the math part of the calculation. So for the math part of the calculation, everything in the numerator gets multiplied, everything in the denominator gets divided by. So to actually get our final answer, we would take 315 times 6.02 times 10 to the 23rd, divided by 1,000, divided by 12, and we would get our final value, rounding to 3 significant figures because that's where our initial information was. 315 milligrams is 3 significant figures, so our final answer should be rounded to 3 significant figures as well. We'd be looking at 1.58 times 10 to the 22nd atoms of carbon. We say, okay, is that answer reasonable? That's a lot of atoms of carbon, but we recognize atoms are so small that it's going to take an awful lot of them to come up to 315 milligrams. So let's look at another example. Next example is kind of almost the exact opposite. Here we're starting with how many atoms of an element we have. We want to figure out what is the mass of that sample. What is the mass of that element? So here we're starting with 5.78 times 10 to the 22 atoms of iron. What's the mass of that many atoms of iron? Now, we're going to start with our given information, 5.78 times 10 to the 22nd. And I want to go from atoms, I'm trying to get to, atoms is a counting number, trying to get to grams. So I'm going to go through moles again. So that's going to be my first step, is to go through moles. Well, how can I go from counting number to moles? That's using that counting definition of the mole. 1 mole is 6.02 times 10 to the 23 atoms. I'm starting with atoms in the numerator, so I want atoms in the denominator. So atoms in the numerator, atoms of iron will cancel. Now I'm going to be left with moles of iron. If I want to go from moles to a mass, where am I going to look? I'm going to look at the periodic table for that molar mass. We find iron on the periodic table. Its average mass is 55.85. Well, that's the molar mass of iron. That's how many grams it takes to give you 1 mole of that substance. I want the moles to cancel, so I'm starting with moles in the numerator. I'm going to put the moles in the denominator next step. Moles of iron will cancel. The unit I'm left with is the unit I want, which is grams of iron. Now it's just a matter of doing the math. So for the calculation, everything you see in the numerator is a multiplication. So 5.78 times 10 to the 22nd times 55.85. Then you're going to take that and divide it by the 6.02 times 10 to the 23rd. When you round that to 3 significant figures, you should be looking at 5.36 grams of iron. Now, a couple of things when you're trying this. So when you're going through and you are trying this on your own and doing some of these calculations, whether it's this one or a similar one, if you end up getting a very strange answer, it might have the right number here, but you get a crazy exponent. Something like times 10 to the 44, times 10 to the 46, or 10 to the 47. What that is an indication of is that the calculator is not reading the scientific notation you entered in the way you think it should be. It ended up multiplying some things that were really divided by. So just something to think about when you're practicing these. If you're getting all sorts of crazy exponents for a problem like this, you might need to go back and look at the instruction manual in your calculator, make sure you're putting in scientific notation in the way that your specific brand of calculator is going to deal with that correctly. So we did a couple examples with atoms and elements, but when we think about all the different matter that's out there, most of the matter we deal with is not just a pure element. We're much more likely to be dealing with a compound than we are just a pure element. So we want to talk a little bit about molecules and compounds. Everything we just did for atoms will also work for molecules and compounds. We just have to treat the molecule or compound as a total collection of the atoms or the ions. The total for a molecule or a compound is going to equal the sum of all the individual parts that make up that molecule or compound. Kind of makes sense. If you care about the total of something, add up all the individual parts. After you've added up all the individual parts, it has to tell you something about that total. I'll do some examples of dealing with molecules and compounds. The first one I want to deal with deals with figuring out the molar mass of N2Br4. So this is a molecule. We want to figure out what that molar mass is. How many grams of that substance do we need to make a mole? And for this, we just have to sum up the individual pieces and figure out how many of which individual pieces we have. Well, according to subscripts, we have 2 nitrogens. So each nitrogen comes in at 14.01. Now we look at our bromines. We have 4 bromines. So we're going to want to put out 4 bromines. Look up the mass for the bromine at 79.9. 1, 2, 3, 4 bromines. If we sum together all of these, all the individual parts that we listed, we're going to get the total. So the sum total for N2Br4 is 347.62. Now, what does that 347.62 really mean? That 347.62 is really the molar mass of N2Br4. It's how many grams of N2Br4 it takes to give you 1 mole. So 347.62 grams of N2Br4 is equal to 1 mole of N2Br4. Let's do another example dealing with molecules and compounds. This is a compound, molar mass of Mn2SO45. Well, here, sometimes you may not want to list out everything individually, but you still have to count the pieces correctly. So I have manganese. Manganese on the periodic table comes in at 54.94, but how many manganeses do I have? I have 2, so I need to multiply that 54.94 times 2, and that's going to give me the 109.99. For the sulfur, now we're looking at the sulfur here. Sulfur, we look on the periodic table, 32.07. Well, okay, so we got that. How many sulfurs do we have? Well, sulfur is part of this polyatomic ion. Here's where we're using those parentheses again. Each unit of sulfate has 1 sulfur in it, and I have 5 units of sulfate, so I'm going to have 5 sulfurs. So I'm going to take the mass of the sulfur, multiply it by 5 to give me my total for my sulfur. Now for the oxygen, how many oxygens do I have? Well, oxygen comes in at 16 on the periodic table, but how many do I actually have present in this compound? Well, in this compound, each unit of the sulfate gives me 4 oxygen atoms, and I have 5 of those units, so 4 times 5 is going to give me 20 atoms of oxygen. 20 times 16 gives me the 320. I sum together all the parts, and I'm going to get 590.34. What's that 590.34 really represent? Well, that's the molar mass of Mn2SO45. That means it takes 590.34 grams of that substance to give us 1 mole of that substance. So when you're dealing with a molecule or a compound, all you really need to do is sum together all of those individual pieces. So we're going to do some more examples of actually using this in our calculations. So dry ice is sometimes used in shipping perishable foods to keep the item frozen or cold. What dry ice actually is it's solid CO2. So what we want to determine is how many molecules of CO2 are present in a 1.5 pound brick of dry ice. So some useful information was provided for us. 2.2 pounds equals a kilogram. So we got a way of converting between the English and the metric. Again, this is a dimensional analysis problem. We need to use dimensional analysis in order to solve this. So what do we start with? Well, the only thing we could really start with is the pounds of the CO2. So we have our pounds of the CO2 ready to go. I know I can't do anything really useful in those English units. I have to convert to metric. Well, I was given a way of converting between the English and the metric here. So I'm going to go ahead and get out of English and get into metric right away. Pounds and kilograms, I want to get away from pounds. I have pounds in the numerator already. So I want my pounds in the denominator. So kilograms in the numerator, pounds in the denominator. My pounds of carbon dioxide are going to cancel. Now I'll have kilograms of carbon dioxide. Well, I know to start working in mole units, I can't be in kilograms, I have to be in grams. So I need to do a metric to metric conversion. Remember, these metric to metric conversions aren't provided. So you need to come up with these on your own. So go from kilograms to grams. I need the conversion. Well, it takes 1,000 grams to give me 1 kilogram. I want to put the kilograms in the denominator to cancel with the kilograms I already have in the numerator. So 1 kilogram of CO2. Numerator, kilograms of CO2 in the denominator are going to cancel. Now that I have grams, now I want to go to moles. So from grams to moles, how am I going to get there? When we go from grams to moles, what we need is the molar mass of that substance. So we've already done this for elements, now we're ready to do it for compounds. So I need the molar mass of CO2. Well, how did I get the molar mass of CO2? And on the side I did this work. So on the left-hand side, I just summed together all the pieces that go into making CO2. CO2 has 1 carbon. It comes in at 12.01. CO2 has 2 oxygens, each one coming in at 16. So the total for CO2 is 44.01 grams per mole. I'm now using that as a conversion factor. Just like I use it for an individual element, now I can just use that for molecules and compounds as well. So I decide what I want to go away. I want the grams to go away, so I better put the grams in the denominator. Grams of CO2 cancel, leaving me with moles in that numerator. Now I want to go to molecules. Well, that's a counting number. So what's my conversion for a counting number? Well, moles and a counting number get related by that 6.02 times 10 to the 23rd. Here I'm not dealing with atoms, I'm dealing with molecules, because CO2, that unit is called a molecule. So 1 mole of CO2, 6.02 times 10 to the 23rd molecules of CO2. Moles in the numerator will cancel with moles in the denominator. The unit I have left is the unit I want. The only one I didn't cancel off is the molecules of the CO2. So now I'm ready to actually do the mathematical calculation for this. Remember, for these dimensional analysis problems, anything in the numerator is a multiply by. Anything in the denominator is a divide by. So I'm going to take my 1.5, you don't have to multiply by 1, but multiply by 1,000, multiply by 1, multiply by the 6.02 times 10 to the 23rd. Now we're going to start the divisions. Divide by everything you see in the bottom, in the denominator. Divided by 2.2, divided by 44.01. We're going to take our answer. We're looking at two significant figures for this. So when you round this to two significant figures, you'd be looking at 9.3 times 10 to the 24 molecules of CO2. We ask ourselves, does that make sense? Well, if we're trying to count how many molecules are in a pound-and-a-half brick, it better be a pretty large number of molecules, knowing how small molecules actually are. So this answer seems reasonable for us. So you're going to treat molecules and compounds the exact same way we did for the atoms and the elements before, except you might have to sum up all the individual pieces to figure out what's going on with the total. Let's do one more example using this time a compound. This one asks a little bit different question. So this one asks, how many atoms of oxygen are present in 436 milligrams of the calcium nitrate that we see here? For this one, here we're not looking for how many units of the calcium nitrate, but how many oxygen atoms are within those units. So this starts off very similar to the other ones. The only real starting piece of information we can start with is the milligrams of the calcium nitrate. I know I can't leave them in milligrams. I have to get to grams, so I need to do a metric to metric conversion in the next step. Milligrams and grams, it takes 1,000 milligrams to equal 1 gram. I want to place the milligrams in the denominator, so they'll cancel with the milligrams in the numerator. So now my milligrams of calcium nitrate are going to cancel. Now I'm going to have grams of calcium nitrate. Well, I need to go from grams to moles. So how can I go from grams to moles? Well, to go from grams to moles, what I'm going to have to do is I'm going to have to use the molar mass. I'm going to have to sum together all the individual pieces. So I just rounded calcium to 40 just to make it a little bit easier. I have one calcium coming in at 40, two nitrogens. I could have rounded that to 14 as well, but I didn't. Nitrogen comes in at 14.01 times 2 for 28.02 for the nitrogen. How many oxygens do I have? Well, in each unit of calcium nitrate, I have 3 oxygens. I have 2 units of nitrate. So I'm going to get 3 times 2, or 6 units of oxygen coming out. 16 times 6 is going to give us our 96. So we're going to sum together all of our pieces. We're going to sum together all the pieces. The 40 from the calcium, the 28.02 from the nitrogen, the 96 from the oxygen, to give us our total of 164.02 grams per mole. That's the molar mass for calcium nitrate. Now I can use that. That's how many grams it takes to give me 1 mole. I want to move away from the grams, so being I'm moving away from the grams, I'm going to put the grams in the denominator such that they're going to cancel with the grams in the numerator. Grams in the numerator cancel with the grams in the denominator. Now the unit I currently am at are moles of calcium nitrate. Well, what can I do with moles of calcium nitrate? I can now start working towards getting to that counting number. I ultimately need a counting type number, atoms of oxygen. Well, I got to start getting to that counting type number. Well, that actual counting number, there's only one way to go from moles to that counting number, and that's to use Avogadro's number. That just definition of a mole. 1 mole is 6.02 times 10 to the 23rd, regardless of what you're dealing with. Here I'm calling these units of calcium nitrate. It's not really molecules because it's an ionic compound. Usually we don't call ionic compounds molecules, so I'm just going to leave it as units. 1 mole is going to be 6.02 times 10 to the 23rd. I want moles to cancel, so moles in the denominator are going to cancel with the moles in the numerator. And the unit I'm currently going to be at are units of calcium nitrate. Now that's not ultimately what I want to achieve. Ultimately, I want to figure out how many atoms of oxygen I really need. Well, so I need some relationship between units of calcium nitrate and atoms of oxygen. Well, here's one. This is probably the most difficult step to actually see when you're doing this problem, but it's also a step that you've actually already done in an earlier part of this problem. If I have 1 unit of calcium nitrate, how many units of oxygen do I have? Well, we kind of already answered that. If you go back down to the lower left-hand corner when we did the molar mass, we kind of already answered this question. 1 unit of calcium nitrate, we already determined had 6 oxygen atoms that go into making that up. Well, any true statement you can write can be used as a conversion factor. So 1 unit of calcium nitrate in our last step contains 6 atoms of oxygen. That's a true statement. Any true statement you can make can be used as a conversion factor. I want the calcium nitrate to go away, so that's going to be in the denominator, such that units of calcium nitrate are going to cancel. I'm going to be left with atoms of oxygen, which is what I ultimately want. That's what I want to be left with, are these atoms of oxygen. Last step is to just go through the mathematical calculations for this. Multiply everything through the numerator, 436. We don't need to multiply by 1, but then multiply by the 6.02 times 10 to the 23rd, then times 6. Then everything in the denominator is a divided by. So divided by 1,000, then divided by the 164.02. We're looking at rounding our final answer to 3 significant figures because we started with 3 significant figures in our initial part, so we should round to 3 significant figures at the end. And then at the end, we're going to get 9.6 times 10 to the 21 atoms of oxygen. Now again, we have to ask ourselves, is this reasonable? Is this kind of what we would expect? We got a very large number. Should we get a very large number? 9.60 times 10 to the 21st is a very large number. Is that reasonable? And here, yes, that is reasonable. I'm trying to figure out atoms of oxygen present in 436 milligrams. Even though 436 milligrams isn't a lot of material, we know just how small atoms actually are. It's going to take a lot of atoms to get anywhere close to that amount of material. So here, the key things that we're doing in these examples that we did in this presentation is you saw that we used both definitions of the mole. We ended up using the counting definition of the mole. We use that in a couple different places. If I highlight that in purple here, we used that. We use that counting definition. That's 6.02 times 10 to the 23rd. What you also see, I like this in green for you, what you are also seeing is we're using the counting by weighing definition of the mole. So using that counting by weighing definition, we're using the molar mass. You see that in the green. You see this in all the different problems that we did. We used both of the definitions of the mole. And now we're at the stage of we're doing chemistry problems using this dimensional analysis technique where we're arranging our multiplications and divisions such that units are canceling off. Then at the end, we're multiplying things across the numerator, and then anything in the denominator, we're dividing through by this. So this was our introduction to the mole. We're going to be doing some other calculations using this. So key thing is this is just the beginning of our mole type calculations. We use mole for a lot of different things. Make sure you have a handle on these basic mole calculations, because we're going to use some of these repeatedly over and over and over again, especially that counting by weighing definition. You're going to see you're going to be using this all the time in chemistry. It just never goes away.